All right, we're at the point in POE now where we're going to solve an entire truss. We need to find all of the external forces acting on the truss. In this case, two different external forces have been provided for us. These are the loads put on the truss. But we also want to find the external forces provided by these supports. We have a roller support over here at joint A and a pin support over here at joint C. We want to find out what those reaction forces are under this loading situation shown here. We also want to find the internal force in each member of this truss, because as an engineer we are responsible for making sure that the truss we design, the materials we select for those members, and the dimensions of those members are all going to be able to withstand the loads that we think the truss will have to withstand. So that's the purpose. Let's go ahead and get started on solving a truss. First thing we want to do here in step one is replace all pins and rollers with their appropriate reaction forces. So this roller here, I'm going to erase that in a second. Rollers only provide reaction forces perpendicular to the surface they're on. So in this case, the vertical direction. I always tell my students to draw their reaction forces in the positive direction. So when we're talking vertical, the positive direction would be upward. That seems to clear up a lot of sign errors that students would make. That's a reaction force at joint A in the Y direction. We'll want to find that in just a moment here. Pins provide reaction force in the vertical direction and the horizontal direction. So I'm going to erase that pin, put the reaction force at C in the Y direction. I drew it in the positive vertical direction. It's also going to provide a horizontal reaction force. I'm going to draw that in the positive X direction, which is to the right. Reaction force at C, in the X direction. All right, so we're all set up. We're ready to solve. Our first thing we have to do is find out those external forces, RAY, RCY, and RCX. Before I even jump into that, I want to make sure this truss is statically determinate. Can it be solved, or will there be some built-in forces within these members that we can't account for? Let's check and see if it's statically determinate. To determine that, we're going to look at this equation here. 2 times the number of joints equals the number of members plus the number of reaction forces. We want to determine if that is in fact true. If it's true, it's statically determinate. We'll go on and solve the rest of the problem. How many joints do we see? Joints are where members come together. So we have members coming together A, B, C, and D. There are 4 joints. Members, that would be like the piece of wood making up the truss. So we have member AD, AB, BD, CD, and BC. So there's 1, 2, 3, 4, 5 members. This whole bottom piece is not one member. Every time you get to a joint, it starts a new member. Reaction forces. Now we're not talking all external forces. We're talking about just the reaction ones from your supports. So we have 1, 2, 3 reaction forces. 8 equals 8. Yep, it's statically determinate. Let's go ahead and solve this thing. We've got to solve for those external forces now. Since this thing is in static equilibrium, it's stationary, we can use our 3 static equilibrium equations. Sum of the force in the x direction has to be 0 since this truss is not translating to the right or to the left. The sum of the forces in the y direction also has to be 0 because this truss is not translating up or down. And the sum of the moments about some point also has to equal 0. You can pick any point. Certain ones work better than others, and I'll tell you about that in just a moment. Let's start here. Let's sum the force in the x direction. What forces do we have in the horizontal plane? Let's see. That's vertical, vertical, vertical. There's a horizontal one. RCX, and it's to the right, which is the positive x direction. So it's positive RCX. This force is also in the x direction, and it's to the right. So it's plus FD. And those are the only 2 forces in the x direction. So those 2 have to add up to give me 0. Let's plug in the values we know. We don't know RCX, but we do know FD is 2,000 pounds. So subtract 2,000 from each side. RCX is going to be negative 2,000 pounds. As soon as you know that box in, so it stands out, and go up and update your free body diagram up top there. RCX, negative 2,000 pounds. Now that's one you probably knew before you even started. If there's 2,000 to the right on the truss, there's only one other X force. You might have known that was 2,000 that direction. But again, I'm trying to teach my students to not make sign errors, and the conventions I teach about always moving in the positive direction seem to clear that up. But it does seem to match with what I would expect. 2,000 that way if it's going to have to be 2,000 that way. I'm not going to change that mid-problem. I will take care of that when I redraw my truss down here in a second. I'll flip the arrow around. All right, some of the forces in the y direction. Let's see, I have RAY, and that's up, so positive RAY. I have FB in the y direction, but it's down, so minus FB. RCY is up, so that's the positive direction, RC plus RCY. And those are the only three forces in the vertical direction, so we'll have to add up to 0. Let's plug in what we know. We don't know RAY yet. We do know FB is 100 pounds. We don't know RCY yet either. So I have an equation with two unknowns. I can't solve that yet. I'm going to move on, do the third static equilibrium equation, and then come back, and I'll have found one of those two forces over here in the moments part. So I'll come back to this in just a moment. Let's sum the moments about some joint. What would make sense here? To minimize the number of moments we have, I'm going to pick the pin as my fixed point. The reason for that is that any force that goes directly through that is not going to cause this thing to rotate, as you saw in the external force video. So let's choose joint C as our fixed point. So this force will not cause rotation. This force will not cause rotation. But each of these three will, because those forces are all offset from our fixed point right here. So we're going to have three different terms in this moments equation. Just to remind you that to calculate a moment, it is the magnitude of the force times the distance perpendicular to the line of action of that force. I teach this maybe a little differently than you have seen in other videos, but it seems to help my students, again, not make the sign errors that many of them tend to make without these little tips here. So let's sum the moments. Here's our fixed point. Let's start with RAY. That's going to cause clockwise rotation about this point here, and clockwise is a negative direction. So negative moment from whatever is occurring at joint A is how I teach that to my students. Clockwise rotation is a negative moment. Move to this force. Force B, if this is my fixed point, force B is going to cause counterclockwise rotation. So that's the positive moment direction. So the positive moment from whatever is occurring at B. And the other force that's causing rotation is force D. That's going to cause this to rotate clockwise. That's the negative moment direction as well. So negative moment from what's occurring at D. Those are the three terms. Those have to add up to 0. Now I'm going to take each of these moments and expand them out using this equation, force times distance perpendicular. So negative moment from A. What's the force at A? It's RAY. We don't know its magnitude, but it's RAY. And the distance away from the fixed point, all the way over here, that's 14 feet away. Plus, okay, the moment at B, the force is 100 pounds. I'm not putting a negative 100 because in this column we're looking at moments. We're not looking at the direction of forces. So a negative in this column means clockwise. A positive means counterclockwise. And we took care of all those signs here, so we're not going to see those show up down here. So 100 pounds times how far away is that from the fixed point? That's 4 feet away. Minus, okay, the moment from D, the force is 2,000 pounds. Times the distance perpendicular to the line of action. Now this one's the one that's a little bit trickier. That is the line of action of the force. So the distance from here, perpendicular to that, is that distance right there shown with my finger. And that distance is 7 feet. There we go. Only one unknown, so I can solve this. So negative 14 RAY plus 400 minus 14,000 equals 0. So negative 14 RAY equals 13,600 by bringing these two terms over to here. Divide by negative 14, and RAY comes out to be negative 971 pounds. So I'm going to go back and put that on my diagram here. RAY negative 971 pounds. The negative tells me I drew it in the wrong direction. No big deal. I'll flip it around when I redraw my diagram. I'm going to do the same thing here. I'll flip that arrow around later once I redraw my free body diagram. All right, all I have left is to find RCY, which I can find with this equation here. I just found RAY, so let's take that value and plug it in right over here. RAY is negative 971 minus 100 plus RCY equals 0. And let's solve for that. Add 971, add 100, and you get RCY to be 1,071 pounds. All right, so we've found the external force. It's always good to go back and double check and just make sure your answers make some sense here. In total, there's 100 pounds down. So these two forces have to add up to 100 pounds up to keep this thing stationary. Now the result might not be what you expected, but this plus this does give you 100 pounds up. Horizontally, we have 2,000 pounds to the right. This tells us we have 2,000 pounds to the left, so we're feeling pretty good about our external reaction forces. It's always good to double check those, because if you make an error anywhere in here, and this is the main place people make errors, then everything beyond this that uses that number is going to be incorrect. So, all right, we're all set. Now, next thing we need to do is find out some angles in this, because we're going to have to use some angles to find our internal forces. Which angles do we have to find? You kind of learn that by experience and by doing some trusses. I'll kind of talk you through my thought process, but the only way to really get better is to do a couple on your own. Here we go, let's check it out. When we look for the internal forces in a truss, I'm going to flip this sheet over here. We're only going to have two static equilibrium equations available to us because we're going to be drawing a free body diagram for a joint or a single point. All forces will be going directly through that point, so there won't be any moments because none of the forces will be offset from that point. They'll all be going straight through that point. So if there's only two equations we have available to us, we can only have two unknown values. So this might not make sense until you see one, but I'm going to go through point by point and just tell you what my thought process is here. If I'm going to draw the free body diagram for joint A, I know this force, but I'm not going to know the force provided by member AB or the force provided by member AD. Two unknowns, we'll have two equations, so I could go ahead and start at joint A. So finding this angle, angle A, might make some sense. Let's call that theta A. Joint B, I know this force acting on joint B. I don't know the force from BC or the force from BD or the force from AB. Three unknowns. So I'm not going to start that joint, but I do know these angles are right angles already. So I don't need to go find those. C, I know this force, I know this force. I'm not going to know that force or that force. Two unknown forces. I could start at joint C. So finding that angle, let's call it theta C, might be a good thing for me to do. This angle here and this angle here, let's see, if I choose that joint, I know that force, but I don't know this member's force or this one or this one. There's three unknowns there. I definitely don't want to start there. I can't. And I really don't want to go to joint D at all unless I absolutely have to, because there's a couple different forces at angles, and that's where the problems get a little more complex. So I'm going to avoid joint D as long as possible. Maybe I don't even have to go there. So anyways, all that to say, let's find this angle A and this angle C. You could go ahead and just find them all at this time if you wanted to, but we'll just find those two. We're going to use some basic trig. We're going to use the distances that we know. So looking at this triangle right there, triangle ABD, I know, in reference to that angle theta, A, I know the opposite side is 7 feet. I know the adjacent side is 10 feet. What trig function has opposite and adjacent in it? That'd be tangent, SOHCAHTOA. So I would write tangent of theta equals the opposite side from here is directly across, it's 7 feet, over the adjacent side 10 feet. Solve for theta. So theta is the inverse tangent of 7/10, and that gives me theta A. So theta A equals 35 degrees. I also want to find theta C. So now I'm going to look at that triangle there, triangle CBD. I know the opposite side is 7 feet. I know the adjacent side is 4 feet. So trig function with opposite and adjacent is tangent once again. So tangent of theta C equals the opposite side is 7. The adjacent side is 4. Theta C equals the inverse tangent of 7/4. So theta C comes out to be 60.3 degrees. And those seem reasonable based on my diagram up here. All right, step 5. Now we're going to redraw the truss showing all external forces and angles. We no longer need the distances. The distances up here were used in the moment equation, and they were used to find our angles, but we won't use those anymore, so you don't need to clutter up your next redrawn picture with those. So let's get to this here. We've got this truss, joint A, B, C, and D. We've got force D, 2,000 pounds. We've got some other external forces that we're going to put in here. Let's go ahead and put our angles right now. Theta A we found to be 35 degrees, and theta C we found to be 60.3 degrees. Okay, other external reaction forces. Now at this point, we want our diagram to represent the situation as best as possible. So if we got a negative force up here, that means we had drawn our arrow in the wrong direction. So we're going to flip it now and make it positive, make it realistic. We don't want to change those negatives mid-problem, but when you're going to redraw the entire truss, that's when it's okay to do that. So RAY is negative 971 in this direction, which means it's actually positive 971 in the downward direction. So I'm going to draw RAY is a positive 971 in that downward direction. We still have force B, 100 pounds down. And then at joint C, we had our CX and our CY. Our CY, we drew it up and we got a positive number, so it is in fact in the upward direction. So let's keep it that direction. Our CY is 1,071 pounds. Our CX, we drew it to the right, but we got a negative value, which means we drew it the wrong way. So we're going to change our arrow and point to the left and make it 2,000 pounds. Our CX is positive 2,000 pounds, but in that direction shown by the arrow there. All right, so we have now redrawn the truss with all external forces and angles, and we've labeled the joints. Now we're ready for the internal forces. Let's flip this over and continue from there. I'll be flipping back and forth a little bit. Hope you don't get dizzy seeing this part here. All right, internal forces. We are going to use our two static equilibrium equations for the joints that we determine are the most helpful for us. The approach you take might be different than the approach I take. How you go about it and what joints you choose, that can vary. But here's just one example of that. I'm going to start with joint A. The reason is I know one force there. There are two unknown forces, so I'll be able to find these two internal forces from this work here. So let's draw the forces acting on joint A. All right, what do we have? Let's see. We have RAY downward at 971. Let's go back to other forces we have. We've got, if you can cover up the rest of the truss, if this might help you out. The only things touching joint A would be the roller support there and these two members. So those are the only three things that can apply forces. So we're going to have a force in the horizontal plane and a force here at an angle. Now we're going to assume that all joints are in tension. I'm sorry, all members are in tension. They're all being stretched out. So what direction is the force acting the joint? I'm not sure how well this will work for you here, but we're looking for the force acting on joint A. My finger there represents joint A. I'm going to put this rubber band, which represents member AD, I'm going to put that in tension. I'm going to pull on it this direction. So if the member, the rubber band, is in tension, what direction is it applying a force to my finger here at joint A? Which way is it pulling that finger? Yeah, it's wanting to pull it this direction. So members are always going to be pulling out. We're going to assume that. It might be wrong, but that's how we're going to do it. So we've got this force from member AD, which we don't know. We've also got a force from member AB, and that's pulling directly to the right. Now these reaction forces, these external forces, those don't always have to be coming outward from there. However they're drawn here, that's how we'll draw them on our free-body diagram. But the internal forces in the members, we're always going to assume tension, so we're going to always draw those outward from the joint. All right, so we're ready to get started. We need to know this angle right here. That was 35 degrees. All right, how do we proceed? Well, whenever you have a force or a vector at an angle, you want to break those up into components. So that's all in the x direction, that's all in the y direction, but AD is partially in the x, partially in the y. So I'm going to have to break that up into its x component and its y component. Let me get that focus there for you. All right, I'm going to try to zoom in a little bit here. All right, so this vertical arrow, which is upward, is FAD's y component. And this rightward one, it's kind of getting really muddy in there, that's FAD's x component. Once you draw those components, you ignore the vector that was at an angle. All right, here we go. Sum of the forces in x. What forces are there in the x direction acting on joint A? Well, I've got force AB here, and that's to the right, so it's positive direction. So positive FAB. And I also have part of AD. Its x component is in the x direction. It's pointing to the right as well, so it's the positive direction. So plus FAD's x component. Not all of FAD, just its x component. And those are the only two. So those two must add up to 0. I don't know FAB. I don't know FADX, but to find the x component of a force, since the angle theta is measured to the horizontal, I can use that trig shortcut there. FADX is FAD cosine theta. The x is your cosine. All right, I do know the angle theta, but I still don't know these two unknowns, so I'm going to move on, sum the force in y, and then I'll come back and plug in whichever one of those two I find. All right, in the y direction, what do we have? Let's see, we have RAY, and that's pointing downward. That's the negative direction, so negative RAY. And part of FAD is in the Y direction. Its Y component is pointing up, so plus FAD's Y component. All right, let's substitute our values. RAY is 971. FADY is FAD times the sine of theta, and theta is 35 degrees. One unknown, I can solve that. Turn my page here and find that very quickly. All right, so let's add 971 to the other side. FAD sine 35 degrees equals 971. Divide both sides by sine 35, and you will get that FAD is equal to 1,693 pounds. That's not FAD's Y component, that's FAD. That's this internal force right there. So let's go ahead and quickly update our free body diagram on the other side with that number. FAD, 1,693 pounds. All right. All we have left to find now over here is FAB. We know FAD, so let's bring that over, substitute that in. FAB plus FAD was 1693 times the cosine of 35 degrees. And we solve that. FAB plus 1386.8 equals 0. Subtract that over, and FAB comes out to be negative 1386.8 pounds. Let's go update our picture there, 1386.8. Negative 1386.8 pounds. All right, it's negative. That tells us we assumed the wrong direction. We assumed, let me drop back to this. We assumed that FAB was in tension, was pulling joint A to the right. Well, we got a negative, which means it's actually to the left, so it's actually pushing out on the joint, which means that this member AB is in compression. I'm not going to change it mid-problem. I know the Project Lead the Way PowerPoint shows that. I've found that when people try to change it mid-problem, they end up forgetting to change something else, and they get sign errors all over the place. So we're just going to keep it like it is. We're going to assume tension for every single member, and we're going to roll with FAB being a negative number. I will make that final change at the very end when I redraw the final truss. All right, so let's go back here and come up with our next step in our strategy. We have found 2 of the internal forces. We have 3 left. We have to find BD, CD, and BC. What joint could I go to? You can go to any joint that has only 2 unknowns. At this point, joint D has 2 unknowns, joint B has 2 unknowns, and joint C has 2 unknowns. So you can go to any of them. Again, I'm going to avoid joint D at all costs because they have 2 angles, and I don't want to do those. Those make the problem a little more complex. Joint B looks like a good one to go to. None at angles. You have 2 unknowns. I'm going to go ahead and go to joint B. All right, what forces do we have acting on joint B? We have force B downward, and that's 100 pounds. All right, moving back here. What else is acting on joint B? We have 3 different members. You know, if we cover up the rest of the truss, we have 3 different members acting on joint B. We're going to assume they're all in tension. Now, I know this one is negative, so we actually know it's in compression, but I'm not going to change that mid-problem. I'm still going to draw it as it's in tension. So we have number AB pulling it out to the left. we have member, what was that? BD pulling it up and BC pulling it right. There we go. We do know force AB is negative 1386.8. All right, so let's go with that. Sum of the force in the x direction. I suggest to my students not writing numbers in the very first line. Again, it leads to sign errors here. Just write your symbols. And then when you plug in the numbers, the signs will take care of themselves. All right, so the way I've got drawn, BC is in the x direction, and it's to the right, so it's the positive x direction. AB is drawn to the left, so I'm going to put negative or minus FAB, and those are the only two forces in the x direction. So those two must add up to 0. Let's see if I know any values. I don't know BC, minus. I do know AB is negative 1386.8. So it's minus a negative 1386.8, or minus a negative is positive. So FBC, this is plus, so I'm going to subtract that over there. FBC comes out to be negative 1386.8 pounds. I'll go update my free body diagram of that. Negative 1386.8 pounds. Now I'm going to go ahead and find internal force in BD by sum of the force in the y direction. What do we have? We have FBD drawn in the y direction. It's up. That's the positive direction, so positive FBD. And we have FB in the y direction, and it's pointing down, so that's the negative direction, so minus the external force FB. Those are the only two in the y direction, so those have to add up to 0. I don't know BD, but I do know FB is 100. Which allows me to solve for the internal force of BD. Let's update my free body diagram. Got positive 100 pounds for that. All I have left is to find the internal force in member CD. So I can go to joint C or joint D. Again, I'm going to avoid joint D. So I'm going to go right here to joint C. We've got 4 different forces acting on joint C. We've got these 2 external forces, and we've got 2 members interacting with joint C. So, joint C. Let's drop back here. So we have RCY pointing up, 1071. We have RCX pointing to the left with 2,000 pounds. And then we have 2 members also interacting there. One of them was in the horizontal plane. We're going to assume tension, assuming that it's pulling. And another one was at an angle, and we're going to assume tension there as well. I don't know which ones those were. BC is horizontal, and CD is at an angle. We need to go find that angle. That's 60.3 degrees. All right, and before we start, we need to break any forces at angles into components. The one at an angle is force CD. It's got a leftward component to it. My red pen's dying on me. Got a leftward component to it and an upward component to it. So there's FCDY, and there's FCDX. I'm not going to write those on there because it just muddies up the picture too much. All right, sum of the forces in the x direction. What do we have? actually at this point, we only need to know one more force. Let's drop back here, just kind of refocus ourselves. We know all of these internal forces. The only one we have left to find is CD. This was negative 1386.8. So that's really the only one we have left. Well, since that has an x component and a y component, I really could use either of these two equations to solve for it. It's really personal preference. I'm going to choose to use the y's because you only have this and this one's y component. In the x direction you have this, this, and the x component. Not a whole lot more work, but one more place for an error. So let's do the y direction. Force in the y, we have RCY up, so that's positive RCY. And we have part of FCD, its y component, FCDY here, and that's pointing up. So plus FCD's y component. Those must add up to 0. Let's substitute in what we know here. RCY is 1071. FCD's y component is FCD times the sine of theta, which is 60.3 degrees. Only one unknown, so we can solve for that. We subtract 1071 over there. And then divide by sine of 60.3. And that gives us negative 1,233 pounds. So let's go put that on our free body diagram. Negative 1,233 pounds. All right. So on this first page, we found all the external forces right up here. On the back side, we found all of the internal forces within each member. As an engineer, we need to decide if the members that we choose can withstand the loads they're going to experience. We get to choose the material, we get to choose the dimensions. We just have to be sure that they're going to be able to withstand the loads they're going to experience. All right, very last step. We found all those forces. Now we just have to redraw the entire truss and communicate to people what all the numbers represent. In our final answer, there should be no negative numbers. Only positives. So we already fixed the external reaction forces. If they were negative up top, when we solved for them, we flipped the direction here. Now we're going to do the same thing or a similar thing with internal forces. If we got a positive force, that means that that member was in fact experiencing tension like we assumed. If we got a negative number, that means it was not in tension, it was actually in compression. It was being squeezed together. So when we redraw that, we're going to drop the negative and put compression in there. So that's what we're going towards right there. All right, there's all the external forces. They're all positive, and the directions are shown accordingly. Now for the internal forces, we would drop back here. Let's see, this one was positive, so it is in fact in tension. This one is positive, so it is in fact in tension. The other three are negatives, so we're going to drop the negatives and write compression for our final answer. That was positive, so that is tension. This one was positive 100. also in tension. The other three are all negative. So we're going to drop the negative 12,033 pounds, but we're going to communicate that it was in compression in that way. This one here was a negative. We're going to drop the negative and communicate compression. Same thing here. That was negative. We're going to drop that, communicate compression there. There's our finished truss. We have all of the external reaction forces and all of the internal forces experienced by each member. And that's how you solve a truss. Good luck. Solving a truss is a skill with some strategy behind it. The way to develop and get better at skills is simply to practice. Do some repetition, check along the way as you make errors, seek out what the error was, and learn from it. Good luck.